So addition and scalar multiplication of complex numbers is exactly the same as vectors when we're using these Argand diagrams. One way to think about it is the real component of a complex number is I, and the imaginary component is j. And when I say I and j, I'm talking about the way we define the basis vectors in the vectors unit. So yes, some people do call I j, and that could get a bit confusing, but that's probably why they do it, but it's still not very common. So here I've got two imaginary numbers, a plus bi and c plus di. So here is a plus bi, and to think of it as a vector, you could draw a red line here from the origin to a plus bi. And here is c plus di. Okay, so you can see I've marked them in on the axes. So c in the real sense and d in the imaginary sense makes this one. And it would only take a small amount of algebra for you to check that if I was to add them together as we have done already in this unit, well, a plus bi plus c plus di means I add the real components. So I've now got a plus c for my real component, and I add the imaginary components. So we'd get b plus d to all times I. And sure enough, a plus c is over here, and I have made an error there. That should be a plus c, not a plus b. And b plus d is up here, okay? So it doesn't matter which order you do your addition. By symmetry, we obviously end up at the same point. The other thing to consider is scalar multiplication of vectors. So this point here is a scalar multiplication of our z2, okay? So if I multiply c by k and di by k, we get k times c plus di. I haven't specified what k might be, but you can see how it stretches out here, okay? So that's how we would deal with the addition and the scalar multiplication. So let's have a look at example 11b. We're given two complex numbers here. Z1 is 2 plus I, Z2 is minus 1 plus 3i. And we're asked to place Z1 and Z2 on this Argand diagram. So Z1 is 2 plus 1i, so 1, 2, so that is here. And Z2 is minus 1 plus 3i. So we've got minus 1, 1, 2, 3, Z2. All right, that's nice. We've put those two things there. Let's add Z1 plus Z2 and Z1 minus Z2. And I'm sure by now you'd be confident to just write out the answer as 1 plus 4i. And similarly for the subtraction, you should be able to write out that answer quickly now as minus 3 minus 2i. So if I mark in the Z1 plus Z2, that's at 1 plus 4i. So we've got 1, 1, 2, 3, 4. And the subtraction is minus 3. Oh, I can see I've made a mistake here. That should have been plus 3. Minus 2i, so 1, 2, 3, 1, 2. That's Z1 minus Z2. Now, if I was to draw in like vectors, you could see that adding the vector for Z2 to Z1 gets me to Z1 plus Z2. But similarly, if I drew that vector but going in the opposite direction, we get to the subtraction point. And while they haven't asked us to do one like this, I just want to show you 3 times Z1. Well, that's just equal to 6 plus 3i. So if I can mark that in here, we got 1, 2, 3, 4, 5, 6 plus 3 is up here. Okay, so that's 3Z1. And to extend that out, there's like 2 times Z1 and 3 times Z1. So hopefully you can see exactly how the geometry works here. All right, there's one more to do. It's in example 12 where they've given us the numbers like this. So if I add these two numbers together, the real components become 1 minus 2, so that's minus 1 and minus 2i. So that is minus 1, minus 2, that is here. So the first one is here, okay, so that's 1 minus 4i, and the other one is minus 2 plus 2i. So you can see if I added this blue line to this other point, does move from the yellow point to the point over here, minus 1 minus 2i. All right, so that's just adding and subtracting, and also there is some scalar multiplication in some of those questions. So you should have a go at questions 1, 2, and 3 in the text at this point. All right, I'll see you in the next bit.